Then we move to the next talk. So the third speaker is Dongchao Yang. And Dongchao is a PhD student at the Chinese University of Hong Kong, supervised by Professor Hellerman. Currently, his work focuses on audio text unit audio. And today he's going to share with us the challenges in developing this kind of audio foundation models. Okay, Dongchao, now the stage is yours.
Okay, thank you. Thank you, everyone. And I'm very happy to have this chance to share our development in the universal audio function models. And my name is Dongchao Yang, and a PhD student in the Chinese University of Hong Kong. And my professor is Helen Meng. And in this talk, I will introduce from four parts. And firstly, in the past few years, we are focusing on design and different tasks for different audio modalities. For example, for speech, we have developed such as text-to-speech, voice conversion, speech enhancement, and speaker extraction, and a lot of tasks. And also for the audio and the sound modality, we also developed a lot of tasks such as text-to-music, text-to-sound generation, and so on. So for traditionally, for those different tasks, we try to handle them one by one. And actually, we have get a very good performance with those special models. However, we also found that developing different task model for different tasks is very costly. We need to cost a lot of training and development and the team cost. And also, we are also fail to leverage the shared knowledge among different tasks. And also, inspired by the successful the LLM in the NLP domains, and the GPT-3 models have changed the NLP domains. And so we also have a question, how about our audio domains? So whether we can develop an audio foundation model to solve different tasks in a unified ways. And so towards building a universal audio foundation models, we have two important problems. The first is to find a unified audio modality representation for speech, singing, music, and sound. That's because the audio signal is very complex and diversity. We need a compact, complete, and unified representation because it's more suitable for the modeling. After that, we also need to find a unified audio representation modeling strategy. That is, we need to find a simple and effective modeling strategy to use the large scale data set to help us to get a very good performance. So in the following, we will discuss two aspects. The first is the discrete audio representation. We will discuss which types of audio codec is more suitable as a tokenizer for the audio LLM. And we also discuss the audio modeling strategy. That is, to explore whether it's possible to build a universal audio foundation model with the LLM paradigm. And also, we have pointed out what is the biggest challenge in training LLM-based audio foundation models. And as we know, the neural audio codec such as SoundStream and the encodec have been widely used as the discrete audio representations, and it has been widely used in different audio tasks such as TTS, sound generation, or music generations. So all of us want to ask a question: which type of audio codec is more suitable for as the tokenizer for the audio LLM? Before that, we can review the literature and have two observation. The first is the high bit rate codec model brings a challenge for generative models. For example, this will result in the long sequence problem. And the next observation is the previous work such as audio LLM show that semantic information is more easily to model than the acoustical information by the language models. So based on these two operations, a lot of work has begun towards building a low bit rate and semantic rate audio codec. And recently, many related work have been proposed. to the low bit rate or the semantic rich audio codec. So in summary, to realize a low bit rate target, previous work try to first is try to reduce the VQ layers, such as using a single VQ layer or FSQ to replace the RVQ. And the second strategy is to reduce the frame rate. For example, compress the 1 second audio into about 12 frames, and previous works as a sound stream just compress 1 second audio into 50 frames. Here, we propose the first question. If an audio codec is a low bit rate and has a very good reconstruction performance, does it indicate that is a good audio tokenizer for language model? Our answer is maybe not. And we conduct a simple experiment for 2 types of audio codec. The first is RVQ-based model that use 3 RVQ layer. Another codec is one layer with the FSQ, and from the reconstruction performance, we can see the PASQ shows that just using one layer can get a very high reconstruction performance, and it's a very low bit rate. But during training, we found the token prediction accuracy is very low, and the performance of their TTS model get a very high WER. The WER have more than the 20%, and so it means that only consider the reconstruction performance may not get obtain a good audio tokenizer for the audio AM. So the next question is the semantic information is really important. And our finding is the semantic token is more easy to fit by AM, and we design a simple text to do the audio continuous. That is, we use the semantic token and the acoustic to train the audio AM, and we found that and the semantic token is easy to fit by the language model, and we can easily to realize the audio continuous text. But for if we only use the acoustic token, so that is very hard to realize this target in the same dataset. So if we have know the semantic information is very important. So the question is how to obtain the semantic information for audio codec. Here, previous work shows a lot of ways. In summary, the first is directly to quantize the SSL models such as Hubert and or wave to vector models by VQ or k-means. But the disadvantage is we need to train another decoder to recover those tokens into the wave form. The second way is try to distill the semantic information from the SL model into the first layer of the audio codec. The representative work can be such as the semantic speech cleaner, semantic codec, and the mimic codec. And the third way is try to making the audio codec and AM enjoy the same vocabulary space. That is our designed AM codec. And in the next, I will give an introduction about the AM codec. So the AM codec terms to mapping the audio modality into the token space of the phrase of AM such as LLM-2. And our motivation is our current audio tokens do not have any connection with the text token, so it cannot be directly combined with the pre-trained text AM. So we want to directly mapping the audio modality into the token space of phrase of AM and using the AM's vocabulary to denote the audio tokens, so that each audio can be mapping into a sequence of words, so that AM can understand such a new audio language by several demonstrations with its in-context line. And here we give a detailed analysis. To train this model, we also use RVQ styles, but we force the different layer to encode the different informations. For example, for the first VQ layer, we expect it can encode the semantic information. So we directly distill the semantic information from the LLM. And similarly, the second VQ layer use more tokens to encode the acoustic information, and the last layer and the last VQ layer to ensure a good speech quality. And the important thing is that we set a different scale for different layers. For example, the semantic layer, we think we can use a few semantic tokens to represent it, but for the acoustic tokens, we will use more acoustic tokens. And also, we initialize the VQ codebook with the LLM's vocabulary and fix this codebook during training, so that our audio tokens can be easily to map to the word to the LLM's word vocabulary. So after this training, and we can simply use it for combine with the LLM, and LLM will be fixed and do not do any fine tune or other things. And we just need to write an instruction, and then we quantize our audio into the word sequence, so the word sequence can be easily input to the llama. So after, for example, we can use few short learning to that the model to learn the representation of the audio, so that we can after several demonstration, we can ask a new example to ask the model to decide which type of emotion of this audio includes. And similarly, we can also do another audio understanding tasks with feature learning, such as accent classification, bird sound detection, and language identification, and speech command recognition, and so on. And similarly, we can also use them to solve several simple audio generation tasks. For example, we can start to generate the answer of audio of 1 + 1. And a simple summary, directly aligning the audio token space and the text token was our earlier attempt. It provides a new insight to integrate the semantic information into the audio codec. And in the next part, I wanted to discuss about the audio modeling strategies. And nowadays, there are 3 commonly used audio modeling strategies in generation tasks. That is, the first is LLM-based generative models, and that is transfer the generation task as the next token prediction task. And the second way is latent diffusion-based generative models. And we modeling the continuous latent space with the diffusion or flow matching-based model. And the third is the discrete diffusion model, that is such as the thunderstorm, try to predict the discrete token in NR styles. And in this part, we mainly discuss the LLM-based generative models. That's this talk will focus. So the first problem is it is possible to build a universal audio foundation model with the LLM paradigm. And our answer is sure. And as we described in previous, with the help of audio tokenization, we can transfer the audio data into a unified discrete latent space. And then we can observe the text formulation for different audio-related texts. And we found that we can easily formulate any text as a sequence-to-sequence problem, and both condition and target can be effectively represented by the tokenization, so that we can design a unified framework to building this sequence-to-sequence problem by the decoder-only model. So what is the biggest challenge in training LLM-based audio function models? And our answer is how to effectively modeling the long audio sequence. That is, which means when we use RVQ-based codec, it will bring a long sequence, the long sequence problem. For example, for 20 seconds audio, it will produce a very long sequence. That is very difficult to directly modeling those very long sequence. So the problem is how to effectively modeling the long audio sequence. And we have 2 observations. The first is the long sequence problem mainly from the application of RVQ. And we also found that the RVQ token sequence exists the causality. That means the S token only related to the previous I-1 tokens. Such property is very suitable for the autoregressive predictions. So we developed a hierarchical modeling strategy, and we try to use a global transformer to modeling the temporal information between different parts, and a local transformer to modeling the detailed acoustic information. And we also found that the local transformer is far smaller than the global transformer, which means that it will do not bring a very big inference cost. And we also found that with the help of this modeling strategy, the RVQ problem will not be a problem for the LLM-based models. And here we also compare with the previous modeling strategies, such as the value scaled, that is to train two separate models, and the flatten, that is proposed in Music M, but it is very hard. It has a very high performance, but not suitable for the long audio. Also, we have another strategy as the parallel, that is such as used by the audio gene, but the performance is not very good. And also in the music gene, they propose the delay pattern. This is better than the parallel, but still poorer than the flatten. So, and use the hierarchical modeling strategy, we can enjoy very high performance, and it's very suitable for the long audio. And as you know, the previous work such as Mushi also adopts this similar modeling strategy to building their commercial models. So the sixth question is to building a universal audio fundamental will bring the performance improvement over the single text models, and our answer is yes. And by building the universal audio fundamental model, and we find that it can bring a better performance than the previous single text models. And we also show that scaling with more data will bring a better performance in the LLM-based audio fundamental models. And next, we give the conclusion for this talk. First, for the audio tokenization, and we have found that the audio tokenization plays a very important role in the building the universal audio foundation models, and the compact and complete and semantically rich audio codec is always our desired tokenizer. And also we find that exploring a more advanced codec is also is a future directions for the audio modeling strategies. And we have shown the LLM-based generative method is very effective. And but we can also try to explore other generative methods such as diffusion-based pre-train, or combine both the LLM-based and diffusion-based model is also a good direction to exploring. That concludes my presentation. Thank you for your time and attention.
So any questions from the audience? Any questions? Okay, while people are thinking question, I have one. So, you know, in the first talk, in the end of the talk, Neil said they do not observe the emergent capability of audio language model. So in your experiment, do you have any observation of the emergent capability of the models, or do you have any idea how to make the model have the emergent capabilities?
Yeah, actually, in my experiment, I think when the data scaling is enough, and we can find get a very good performance. But for the emerging ability, I think in current, maybe my data is not enough large, so I do not observe such a very good emerging ability. Yeah.
Yeah. Thank you. Okay.
Thank you, Dongchao. Nice talk. In your conclusion slides, in the future work, you mentioned that one potential work is to develop better, more advanced audio codecs as one of the future work. So can you give some insights in how to designing better audio codebooks to preserve the paralinguistic information like emotion, accents, and things like that?
Yeah, I think it's a good question. And I think if we directly train a codec, so all of the linguistic information will be preserved. But the problem is how to better present it, and so it can be easily modeled by the language model. So I think one of direction is maybe we can direct to, I think maybe a lot of work have tried to do directly to quantize the SSL representation. So and add a decoder to recover this information to the waveform. But the problem is during your try to VQ the SSL, how to make sure those information do not lost. So maybe you need to add a lot of supervised loss to make sure those information will not be discarded during training your VQ models.
Okay, okay, we have a question behind.
Hi, Dongchao. Thanks for the great talk. I have a quick question because I want to ask is for speech we have semantic token and acoustic tokens, and the semantic token is a single layer, so which is good to change timbre information, this kind of things. But do you think for audio or for music, we have similar semantic and acoustic tokens in the future? Yeah, or a single layer is good enough. Thank you.
Yes. I think it's a good problem. So I think for the even for the music, we can also build the semantic token such as the music RM. They also use train several of SSL model using their music data, so they can also get a semantic token for the music data. So I think to building a universal semantic token is also important.
Okay. And any question from the audience? Okay, if not, let's thank Dongchao again for his very insightful talk. Thank you.